we're going to view the specific problem of formalizing ordering preferences in binomials as an instance of a much more general problem, which is developing varieties of probabilistic grammars over some combination of forms, which use the letter F for, and meanings, use the letter M for. So we've actually seen some examples of this. So we've already seen, for example, grammars over forms. Grammars that put probability distributions over some kind of formal element in language, like word strings or syntax trees. We've seen this in n-gram models, in weighted finite state automata, in probabilistic context-free grammars. We've also potentially are interested in another kind of model, which we haven't seen yet before, but we're going to develop today. This is a grammar over possible forms given a meaning that is to be expressed. So imagine this is sort of an internal model of what a speaker has in mind. Maybe we've gotten something close to this when we looked at phonetic category realization preferences. What kind of continuous phonetic properties a particular underlying sound category is going to be realized as. But in our case today, we're going to be looking at the input as a meaning, and the output as some kind of form that expresses the meaning. So it's a little more scaled up than just sound categories. And then we might also conversely think of interpretive grammars of possible meanings given a form. Probability of M conditional on F. Today we're going to be focusing on this form given meaning grammar, and in the specific case of binomials we'll be interested in the ordering problem. So conditioned on an input representation, which you can sort of think of as the content, the overall content that you want to convey in the form x and y without an ordering attached to it, we want to put a conditional distribution on the ordered representation using the coordinator and of x and y. So it could be x and y, it could be y and x. So that's going to be the ordering problem we're going to investigate. So as an example for, suppose that we're trying to linearize to determine the order for the words salt and pepper together. So we would say that that is the problem is specifying a probability distribution on the ordered binomial expression pepper and salt, quote unquote, given the unordered set of words salt, comma, pepper, assuming that those are going to be conjoined together. And since this is an empirical science, we actually want to build models that will put real probabilities on those things. And so to learn the right parameters for those probability models, we're going to need data. Fortunately, binomial data are all over the place in naturalistic use. They're very easy to sample. So this is a subsample of a data set that I worked on many years ago now, Blenor and Levy 2006. And these are just some examples of the binomials in them. And you can see there are all sorts that are in there. And I encourage you to look at the paper. In the appendix, we have the complete list. So now that we're in, we know that we've specified the problem. We have an ordering problem that we specified. We have a data set potentially. Those things are in hand. How do we get to a model? Let's think of the simplest possible case. We'll call this maybe the one constraint model. So we'll just focus on a single ordering preference. For example, the preference for short words to precede long words. So the ordering preference, if we abstract away from the specific words, we might templateize this as describing it as the probability of choosing the short before long ordering given the unordered pair of a relatively shorter and a relatively longer word. And we'll say that there's a single parameter that characterizes this model, and that's the parameter p, which is the probability of choosing that short before long ordering. So p is greater than 0.5. The short before long ordering is generally respected in language, and if it's less than 0.5, it's generally violated. If it's 0.5, it's irrelevant to ordering preferences. Empirically, in the data set that I gave you a sample of just a moment ago, 65% of the samples have the short before long in cases where the conjuncts, the words, differ in length, because not all of them do. But when they differ in length, 65% of the times the shorter before the longer one. How do we relate 65% and p? And that sounds like almost too simple to say anything about, but I want to remind you of the logic relating the empirical number 65% with that value p, which is a parameter in the probability model. We do relative frequency estimation as one means of setting p given the data. The relative frequency estimation procedure says if we observe a 65% preference, and that directly speaks to the parameter like that, then you can just set p is 0.65. Why? Because this is the maximum likelihood estimate. So you have to remember that. This is the principle of maximum likelihood to fit models to data. The maximum likelihood estimate you saw before, and I want to remind you that it has a principle. It turns out that if you choose the maximum likelihood in a binomial, and this is now the binomial distribution, which is an appropriate distribution for modeling binomial ordering preferences in language, the binomial maximum likelihood estimate turns out to be the relative frequency estimate. So as an example, we have, here's some samples, like abused and neglected obeys, medicines and yeast violates this preference, and so forth. Okay, so that's a one parameter model. But we saw that there are many different constraints that seem to have influence in ordering preferences. So we need a model that's a little more flexible than just directly fitting a binomial parameter. And what we're going to use for this setting is what we call logistic regression, which is a very flexible general modeling framework for categorical outcomes like a 0-1 ordering preference, one of two orderings, that may be influenced by multiple features, by multiple things. And logistic regression is this very general framework. It's also very closely related to neural networks, which we're going to get to later on. So logistic regression is a ubiquitous sort of building block, both as a model type of its own and also as a smaller piece in other larger and richer types of models. So what is logistic regression? What I've shown you here, this is the sigmoid curve, also called the logistic function, and it maps between what we're going to call eta, which I'll explain to you in a moment, and a value mu. Mu is a probability of one particular type of outcome. The model of logistic regression is that we define, let's say we have two outcomes that are possible, like I choose one word before the other or the other before word one first or word two first in my binomial. We define arbitrarily one of those two things as the success. And we say that the probability of a successful quote-unquote outcome, which just means whatever outcome I designate it as, that would be what I'm calling success. It's a very arbitrary, it's like a 0-1 decision. It's an outcome of 1 rather than a 0, arbitrary coded. So that is going to have the following form. We're going to define the value eta, which is what we call the linear predictor. And the linear predictor is a weighted sum, i.e. a linear combination of a bunch of predictor features. And these are going to be x1 through xn without loss of generality. Here I have n features. And given the linear predictor, there is a nonlinearity that the linear predictor is passed through to put it into a probability space between 0 and 1. And that nonlinearity is this curve right here. That is the logistic function sigmoid curve. You'll notice a couple of interesting properties about this. First of all, when eta, the linear predictor, is 0, since e to the eta is 1, we would have 1 in the numerator. Sorry, e to the 0 is 1. We would have 1 in the numerator and 2 in the denominator. So we get 1/2. And indeed, when eta is equal to 0, we have mu is equal to 0.5, 50-50. So when the linear predictor is 0, we have a fair coin toss. As the linear predictor increases above 0, the probability gets closer and closer to 1. Asymptotically, it will approach 1, but never get to it as eta goes off to infinity, and vice versa to 0 as eta gets arbitrarily small. So we're going to define mu as the mean, the average probability of the expected value of the outcome. That is the probability of success. So a binomial that has a linear predictor, which puts it, for example, right here, is going to occur in whatever ordering we specified as a success ordering 3/4 of the time. So we can think of the linear predictor as a goodness score. It's how good is that ordering, all things being taken into account. So we have the logistic or sigmoid activation function that plugs into linear regression, or logistic regression. Now, how do we connect logistic regression to data to get the parameter values? Because if we saw a moment ago in this slide, the weighted combination of x's is determined by the weights that are multiplied in the betas, the beta weights that are multiplied into the x's. So we have to talk about how do we set those beta weights from a data set. So the way we do it is we specify first our model, we have our coded predictors, and then we get what it turns out to be is a likelihood surface on which we want to find the maximum. So if we remember that earlier on when we had a single parameter, we had also a likelihood surface. It was easily visualizable in one-dimensional space, and it had a maximum. So if this is my parameter p, then my maximum would be here. And the maximum likelihood estimation says if my data has the highest likelihood for this value of my parameter, I choose that value, and that's going to be my maximum likelihood estimate. P hat sub m l e for maximum likelihood estimate. Okay. But in the two constraint example, it's not so simple. So for example, suppose we have both word length and word frequency. So let's give an example of this. So here are the 6 possible ways of combining the short before long and the frequent before infrequent preferences. So short before long actually can sort of have 3 values with respect to a potential outcome. Either an outcome can obey the preference, that is, a shorter thing comes before a longer thing. It can violate the preference, a longer thing comes before a shorter thing. I'm counting in syllables here. Anger has 2 syllables, spite has 1. Or it can be irrelevant to the preference. Correct and acute is 2 two-syllable words. Regardless of which order I choose, the short one will neither precede nor follow the long one because the 2 are equal length. Likewise with down and out, which is 2 one-syllable words. So that's the short and before long. Frequent before infrequent, no 2 words have exactly the same frequency. So you either have violation or obeying. And so we have 3 possible for short before long, 2 possible for frequent before infrequent. So now recall that for my logistic regression model, my linear predictor would look like a weighted combination of the syllable, the length preference, which we'll call syl, for number of syllable differences, and the frequency preference, which we'll call xfreq. So in order to actually get this closer to data, to plug it in here, I have to actually say what these values that I have in my table correspond to in terms of x values. And so what I'm going to do is I'm going to create a mapping from these values to 0, 1, or negative 1 values. So obeying the constraint will be a positive 1, violating the constraint or preference will be negative 1, and irrelevant for the constraint is going to be a value of 0. Okay, and I choose value of 0 because the weight that no matter how strong or weak the preference is, it should be irrelevant, and so I should be adding in a 0 factor here. Okay, so that's my model. Now, it turns out that actually sets up what we can think of as a likelihood surface. Okay, and a likelihood surface is one, now we're in a 2-dimensional space because we have 2 parameters, the strength of the frequency preference and the strength of the length preference. And our data likelihood are a function of the joint combination of those 2 parameters. And what we have here is a surface where, now there's a contour plot, and so we're sort of looking at the mountain peak in the middle of this plot, and then lower and lower values of the likelihood. And it turns out that that's guaranteed to be the shape of a logistic regression curve, because a likelihood surface is what we call convex, that there's only one maximum. And that makes it actually relatively easy to find the optimum. You just sort of climb around, go generally uphill until you get to the maximum. So I'm not going to get into the algorithmics of how to find the maximum. You can find that in many textbooks on optimization techniques for these kinds of problems. What I want to focus on is that this has a value. It has a value which is that the strength of the length preference is 0.48. The strength of the frequency preference is 0.4. These are both positive numbers. So in general, the data suggests that both of these preferences are obeyed on average. And the length preference is slightly stronger than the frequency preference. We can use that then to, for example, to predict what other binomials would tend to do. So our logistic regression structure we can plug in connected with our fitted model parameters. And so if we go back to these 6 example binomials, our model will predict a value for each of those. It's obviously going to choose the highest possible value for new and modern, the highest possible probability of that outcome, new and modern instead of modern and new, because new and modern it obeys both of the constraints. Lowest value for crochet and knit. And these are the actual empirical values. Okay. So, and you can play around with this yourself. This is how this model is going to work. Okay. And when I fit these a larger set of constraints empirically, this is a different data set, but the same principles. This is the results that we get. So the results turn out, as I said before, intuitively the very strongest constraint is iconic and scalar sequencing. This is such a strong constraint that it will make you think of an implausible world scenario in order to obey the constraint. As I said, if you hear, I read and opened the book, you imagine a scenario in which the person actually read the book before opening it, even though that's a very implausible thing. So in this case, language is really powerful. It can make you think of implausible scenarios just by virtue of a word order. Very, very powerful. What you also see is all of the semantic constraints are more powerful than all of the lexical, phonological constraints. And that's very interesting. So what we see is we actually see sort of what emerges from this is actually an interpretable pattern. There's a hierarchy of constraint preference, and it's the semantic constraints that dominate. And it was this quantitative multiple cross-cutting constraint logistic regression approach that allowed us to see this. This was actually not apparent in the literature before this kind of analysis. Formally, once again, these constraints are the x's, whether they're obeyed or not. They're going to be -1, 0, or 1 values in this model. And these are the betas, the weights of those preferences. And I want to also mention that since we just covered Bayes nets, this has an interpretation. The logistic regression model has an interpretation as a Bayes net. So we can think of each of the individual constraints as being nodes in the Bayes net, and they all are pointing to the outcome, which value mu, which is a deterministic function, and a Bayes net doesn't have anything against deterministic conditional distributions. Mu is going to be deterministically worked out by the linear combination of the x's, and then that linear combination is passed through the sigmoid activation function, and that is deterministic, and then that stochastically gives rise to data. So any particular instance of a binomial with the parameter values, with the predictors, the preferences active or inactive or violated x1 through n, is going to determine a productive preference, and that productive preference in turn will then give a stochastic ordering preference, and that ordering preference is mu% of the time you're going to have that ordering of the binomial come out, not the opposite ordering. And so this is actually just a Bernoulli distribution. And for example, we can look and we can see how good this model is, and it turns out that this is we plot the actual proportion of times that a particular binomial appears in one order or the other versus the model proportion. You can see that it's an imperfect fit, but there's a lot of sense to it. So there's a lot of signal. This is the overall trajectory, but there's some noise as well. And that noise is actually an important source of what we're going to talk about next after we take this break.